Life is all about trust. When you get in a car and you drive around town, you trust that other people are going to stay on the left side of the road, or they're going to stop at a red light or at a stop street, and they, in general, are not going to drive into you. When you get to class, you trust that your teacher is going to teach you the right thing. And hopefully when you watch this video, you trust that I'm going to teach you the right thing. When you go to the bank, you give them your money and you just trust that at some point in future, they're going to give it back to you. Now, how do we know that we can trust statistics? Let's have a look at it. The correlation coefficient. Correlation is a mutual relationship or connectedness between two or more things. So, the correlation coefficient, the R value, tells us about the relationship between two variables. So it could tell us that as one variable increases, the other variable also increases. Or as one variable increases, the other variable decreases. But what's important is it tells us how the two things are linked and how they are going to move together. And the R value is going to be a number between -1 and 1. Let's see what it looks like. So, if you've got a scatter plot over there where every single point falls on the least squares regression line, then that is a correlation coefficient of R equals 1. And we call that a perfect positive correlation. So, an example of that could be the number of units that you sell as a business and your profit. Right? So your profit on each unit is consistent because you set the price. So the more of it you sell, the more profit you get. And that's going to be a perfectly correlated example. Then, if your points on your scatter plot are a little bit looser, they're not quite on the least squares regression line anymore, you have a correlation coefficient of about 0.9. And that we're going to call a strong positive correlation. And an example could be the number of customers that a grocery store has versus the profit. So in general, the more customers you have, the more profit you're going to have. But some customers buy more, like an entire trolley full, and other customers are just going to have a basket with 1 or 2 items in, maybe bread and milk, right? So that's not perfectly correlated. Okay, then if we move a bit further away from the least squares regression line there, we have a correlation coefficient of about 0.5. And now things are a bit more loosely correlated, and we're going to call that a moderate positive correlation. And an example could be your height and weight. Right? So taller people in general weigh a bit more, but it's not perfect because some tall people are really skinny and some short people are built a little bit more solidly, right? So that correlation is not quite perfect, it's moderate. Then, if we get really far from the line of best fit, but you can still see there's a bit of a trend, that would be a correlation coefficient of about 0.2, and that we would call a weak positive correlation. So an example could be the water usage of a household and the number of people who live there. So if more people live somewhere, then they're going to use more water by showering and drinking and cooking. But you know, some people have a pool and they have sprinklers and they waste water, and people with 6 people in the household might be very economical with their water usage. So there isn't like a very strong relationship there. And then if we've got a scatter plot like we've got there, you can't even guess what a line of best fit would look like. There's absolutely no relationship between those points, and that's a correlation coefficient of 0. No correlation, no relationship between the data. And that could be how many fish you catch if you go fishing and the cigarettes you smoked the previous day. Now, whether you smoke or not is not going to influence how good you are at fishing, so there's going to be absolutely no relationship between those two variables. Then, if we've got a negative sloping line of best fit, it means that as one variable increases, the other one decreases, right? So that would be a correlation coefficient of maybe -0.2, and that would be a weak negative correlation. that over there may be correlation coefficient of about negative 0.5, and that is a moderate negative correlation. And an example would be the average time you spend exercising and the days you spend absent from work. Now, in general, the more you exercise, the healthier you are. So if your exercise increases, the sick days you spend decreases because you're now healthy. But it's not a perfect correlation because sometimes you miss work for reasons that have nothing to do with your health, and you can also still get sick even if you exercise a lot. Right? And then that there would be a correlation coefficient of about a negative 0.9, so very close to the line but not quite on it, and that is a strong negative correlation, and that which you see there is a perfect negative correlation, R equals -1. So you might have noticed that when the R value is positive, the correlation coefficient is positive, our line of best fit has a positive gradient. And if the correlation coefficient is negative, then the line of best fit has a negative gradient. And that means as one thing increases, the other thing decreases. Right, now what is the use of the thing? The correlation coefficient tells us how much to trust the line of best fit and the predictions we make from it. So, for example, you've got two scatter plots there, and you can see that both of them have exactly the same line of best fit. But the correlation coefficient for the one is about 0.9 and for the other one is 0.2, right? So if we've got a correlation coefficient of 0.9, we know there's a much stronger relationship between the variables. So predictions that you make with the line of best fit that has a correlation coefficient of 0.9 are going to be far more reliable because there's a stronger relationship between the data. Then we can use our calculator in order to calculate R. Let's have a look. So we're going to hit mode and we're going to select stat because we're doing statistics. And we select option 2 because we're finding the correlation coefficient for a least squares regression line in the form y is equal to a plus bx. Right? And then we've got to input our x and our y values. So Sipho got 66 for x, and for y he got 57. We're going to take great care to make sure that we have the correct x value and the correct y value together. Okay, now that you've got all your x and your y values put into this table, we're going to hit on. And then we hit shift, stat, because we're doing statistics, and we're going to select 5 because this is part of regression. And then option 3 there is going to give us R. So we select 3 and we hit equals, and there we have it. We have a correlation coefficient of 0.9662, or if we round it, 0.97. And there we have it, a R value of 0.97 for that data set over there. Right, now in a previous video, I used that data set in order to make predictions for the physics and maths marks of Natasha and Zoya, right? So what we did is we calculated the line of best fit and we used Natasha's maths mark of 90 to predict her physics mark of 94. And we used Zoya's physics mark of 78 to predict her maths mark of 75. Now, the question is it likely that the marks predicted for Zoya and Natasha are accurate? Can we trust the predictions that we made using the line of best fit for the data over there? And the answer is yes, we can. And the reason is that our correlation coefficient for the data is 0.97, and that represents a very strong positive correlation between physics and maths marks. So, no pressure on Natasha and Zoya there to achieve those marks. Now we can discuss the effect of sample size. Statistics derived from larger sample sizes are more accurate. So let's have a look there. We've got two scatter plots, and both of them have exactly the same correlation coefficient, and both of them have exactly the same least squares regression line. But are they the same? Not quite. We can see that for one of those we've only got 3 data points, and for the other one we've got several more. So if we decide to go do some more research for the scatter plot where we only have 3 data points, we might find that it looks something like that. And that would mean that we were maybe a bit wrong about the correlation coefficient there, and that the relationship between the data wasn't quite as strong as we thought. If we've got more data points, we're less likely to run into this disappointment if we go and do a bit more research. So the more data we have, the more we can trust the inferences we make from our statistics. Then we can look at skewness in scatter plots. Now, if you want to look at the skewness of the x values, what you're going to do is you're going to find a grouping of points somewhere on the scatter plot. And what you're going to do is you're going to record the x values of each of those data points. So we can see on the left there, we've got a greater grouping or a higher density of x values. So our density curve there is going to have its highest point round about where that grouping is. And we can see there that the tail of that density curve goes off to the right. So this data here is skewed to the right. So in whichever direction the tail of our density curve points, that is going to be the direction in which the data is skewed. Now we can do exactly the same thing for the y values. We look and we see, there's a bit of a grouping of points over there. Let's investigate. So we record the y values of all our data points, and we see that at the top there, we've got a greater density of points. There's more points grouped together over there. So our density curve is going to be highest over that point, right? But now because our curve is like upright and not in front of us, it's kind of hard to see in which direction this thing is skewed. So what we're going to do is we're going to pretend that our y-axis was our x-axis. So we're just going to invert the graph, right? So we do that over there, and that would be the inverted version. What would have happened if we put y at the bottom and x on the vertical axis over there, and we find then that the y values were skewed to the left. So the tail of our density curve points off in the leftwards direction. Right, let's summarize what we have done. The correlation coefficient, the R value, tells us about the relationship between two variables. And more data points leads to more reliable statistics. So we can consider both of these factors when we decide whether to trust our predictions. And we also know now that data is skewed when there is a grouping of points away from the center of the scatter plot, and we saw how to analyze and make conclusions about that. And there you have it. Now you have some tools to go check whether you can trust the statistical inferences that you make. Now, I'm not claiming to have a correlation coefficient of 1, but trust me when I tell you that the more you practice math, the better you're going to do at it. So, get practicing.